So let's continue with the rest of the theorems, right? So these theorems or rules that we derive from the original 3 axioms, right? So the first one is about the complement or the not operation, right? So suppose you have an event A for a given sample space S. The complement of that event A, we denote it as A prime, or you can use the notation A's complement AC, right? Then the probability of the complement of A, you can find it by 1 minus PA, right? 1 minus probability of that event itself, right? So what is it? The probability of complement of an event is always 1 minus probability of that event. Now, how do you prove this one? Let's try to draw the Venn diagram and try to prove it. It's not hard when you draw the diagram. So here's our sample space, and here's my event A, right? And where's not A? That is everything outside the circle A, but in the sample space. So this outside of the circle, that is our A's complement or A prime. Okay. So what is the complement? All the elements that belongs to S but not in A, right? So outside A. Now, if you look at this Venn diagram, you can see that A and A's complement, they are mutually exclusive. What does that mean? Mutually exclusive means there are no overlaps, right? Nothing common. So that is the mutual exclusion, right? And if you look at these two events, A and A's complement, if you combine these two together, you can get the whole sample space, right? If you get the circle and outside the circle, both of them additionally, you will get the whole sample space. So you can write it like this: A union A's complement is the sample spaces. That's correct, right? Is that clear to all of you? How we define the sample space? That will be A and A's complement, right? So there's nothing else remaining. So the union of them will make the sample space. Okay. Now let's add the probability for both sides, right? So what will happen if we add probability? Right? So you get probability of A union A's complement will equal to the probability of S, right? But what is the probability of S? The probability of whole sample space, axiom 2. See? The probability of the whole sample space, that is 1, right? And so this is what we did in the previous step. So in our right hand side, we have 1, right? And then when you have the A and S complement, when they are mutually exclusive, you can expand it like this. That's the third axiom, right? So if you want, you can write this is axiom 2, and this becomes, this is from axiom 3. Now what will happen? If you take probability of A's complement, you can take this A to the other side, so you get 1 minus E A. So that is how you prove the theorem 2.3. And you can use this all the time when you know the probability of a certain event. If you want to find its complement or the not of it, you can always do 1 minus that probability of the given event, right? So this is very useful theorem, and we will be using it a lot in probability calculations, right? And the next one, the probability of an empty set or empty event, that is going to be 0 for any sample space, right? So that's obvious because the whole sample space is 1, then the rest will be nothing. So that probability will be 0, right? So how do you prove this one? Again, you can use the Venn diagram and the mutual exclusive concept to take the sample space, the whole sample space and the empty set, they are mutually exclusive, right? If they overlap, there cannot be an empty set, right? So you can write this is same as S, right? To get the union of S and nothing, still the S, right? It's like you add 2 plus 0 is still 2, right? Something like that. Not the same thing, but the concept is like that. Now again, we take the probability of both sides. And this we know is 1, right? And then this becomes PS plus P, the empty set, equals 1. So the probability of the empty set will be 1 minus PS, which is again 1 minus 1, 0. Okay. So you can very easily show this one. And remember, probability of A becomes 0 does not mean that A is always empty, right? So you'll see that later when you do calculations, right? So keep that also in mind as a note, right? Having the probability 0 for an event does not mean that it's always empty, right? So here's the next theorem. If you have two events A and B, and the sample space in the sample spaces, and you can write it as A is contained in B, like this, right? Means A is contained in B, so B is the bigger one and A inside it, right? And it says the probability of A is less than or equal to probability of B. I don't think it should be like this, right? So there's a difference. So this one is called a proper subset, but here it can be equal, right? A either inside B or it's the whole B, right? So these two are different. So in this situation, you have the equal sign. In this situation, you have just the less than. Okay, right. And how do you prove this one? Again, you have to think it as two mutually exclusive events, right? How do you write this one? Now, since we have, let me go to the proof. Since we have we can write B as a union of two mutually exclusive events. How do you do that? Now look at the B. You can actually see that. Okay. Right? So you can actually see that B has this small round that is A, and then the outside, right? So the small circle A and outside of A, but inside B, those two together creates B, right? So how do you write it as a union? Means you have to write down A is there, that's correct. A union. What is this, the donut shape area? How do you write it? How do you write this area? Donut shaped area. So that donut and the hole inside, they will create B. Is it the B intersection A intersection B's complement or B intersection A's complement? That should be B intersection A's complement, right? So here's the whole B and A's complement. So where they overlap, you get the donut, right? So I can write B as A union B intersection A's complement, where B and B intersection A's complement are mutually exclusive, right? So you can write PB equals PA union B intersection A's complement. And then from axiom 3, you can write this as PB plus PA PB equals PA plus probability of B intersection A's complement. Right? So this is from axiom 3. But we know that this is always greater than 0. That is the first axiom. Right? Any probability value, it's either greater than or equal to 0. Right? Therefore, if PB is PA plus something else, if you get rid of this one, you can always write PB is greater than or equal to PA. Right? Or which is PA less than or equal PB. Why? This is always greater than 0. If you get rid of this part, your right hand side is going to be smaller than the left hand side. So you end up with PB greater than PA. Right? So that is how you prove that inequality. Okay? Right. Right. Here's the next theorem. Probability of an event A is always in between 0 and 1. Right? For any event A. Right. So the proof is there. I'll give you a few minutes to go over it. Right, so this is the proof contains or uses all previous theorems, right? So if you look at the first line, A is an event in, let's say event A in our sample space S. So A is always going to be smaller than S, and always it's bigger than the empty set, right? So you can write the empty set is contained in A, it's contained in S. Then you apply the probability for this inequality. So all three terms, you get probability of P and probability of A, probability of S. But you know, this is 0 and this is 1. Those are from the earlier theorems. So you'll end up with PA within 0 and 1. Okay. So that is how you prove the theorem 2.6. Now, if you go back to the third axiom, right, where you have mutually exclusive events, it can be finite or infinite. We add the probabilities together, right? So if you have your sample space S, and it contained of mutually exclusive events, let's say A1, A2, A3, A4, A5, and A6. So the axiom says, according to the axiom, those are mutually exclusive. They do not overlap, and they altogether creates the sample space. So you can write S is the union of AI, I from 1 to 6. So you can take the probability of S to be the summation of the individual probabilities you add them, right? So this means you add PA1, PA2, up to PA6. Okay. But in general, if you don't have mutually exclusive events like this, right? So you can get the addition rule. So that is called the general addition rule. And you all have already used this and seen this, right? So that's the next theorem. If A and B are two events in a sample space S, now we don't say that A and B are mutually exclusive. They can be mutually exclusive or they can be overlapping, right? In such a situation, your axiom 3 now becomes a little bit different, right? In order to allow overlaps, the probability of A union B becomes PA plus PB minus PA intersection B, right? So this is the general addition rule, and you have used it a lot, even in smaller grades in school. That is the general addition rule, right? Can you prove it? Right? So again, the best way to do it is to figure out mutually exclusive events in this setup and then proceed with the three axioms, right? Usually it will be the second and the third axiom that you will be using, right? Okay. Shall we draw the Venn diagram? You can see the mutually exclusive events. So now we don't say, or we don't have any restriction about mutually exclusive or anything, just two events A and B, right? So you can see the overlap here, right? So what is this? A intersection B. Okay. So if I write down these areas, okay, this is A, let's say small a, and this part is B. And let's say this part is C, right? So your A union B, you can split it into three different mutually exclusive areas, right? So what are they? Here's our B, A intersection B, this is B. A intersection B's complement, A intersection B's complement is this part. Then B intersection A's complement is this part. Okay? Right? So you can see those three. Okay? So let's try to prove this one. Our A union B is A union B union C. These are mutually exclusive. Okay? So if I write probability of A union B, you get probability of this A. Now my small a is this area, right? Plus PB plus PC. Okay. Now before that, I can do something like this. I'm going to add and subtract a certain value so I can combine, right? Because if you combine A and B, what do you get? If you combine A and B, what do you get? It's red colored area and the black one. A plus B, what do you get? That is A, right? And if you combine or if you add C and B, what do you get? You get B, right? Now you have A, B, C, but there's extra B right here. If you want to write this whole thing as probability of A and probability of B, if you want to do that, you need extra B. Right? So shall we add it? What I'm going to do is I'm going to add it like this, A, B, C, and I'm going to add another B. And when you do that, you have to get rid of it. So I add and subtract B, right? So when you do plus B and minus B, it's like you didn't do anything, right? Now what do you have? A and B, you have capital A. B and C here, you have B. And then you subtract B, that is B, A intersection B, right? So you get probability of A plus probability of B minus probability of A intersection B, right? Okay, so that's one way to prove it, but you can come up with other different ways to do that, right? So this is one way of proving the addition rule. You can even argue it like this. When you are finding the union of A and B, you have PA, you have PB, and when you do that, you add this intersection area or the overlapping area twice, right? When you get the circle A, you have A intersection B. When you get circle B, again you have the intersection area A intersection B. So when you add PA and PB, you add this intersection twice, right? So in order to get rid of that extra A intersection B, you subtract it. So you can argue it in that way also, right? Either way, well, you can prove that the A union B is the probability of A plus probability of B minus probability of A intersection B. Okay, right. So let's do an example. You can either use the rule or you can draw the Venn diagram and figure it out. It's totally up to you, right? So try to find out these or figure out what are these probabilities given. If you want, draw a Venn diagram and put them inside the circles or whatever the areas and solve it. Or straight away, you can use the addition rule. Anybody who has the answer? How do you do this? Okay. So if you look at this scenario, in a large metropolitan area, let's say a city, the probability that a household owns a color television set, a black and white television set, or both, those probabilities are given 0.86, 0.35, 0.29 respectively, right? You have to find the probability that the family owns either or both kind of sets. What does that mean? Right? So what are the two events here? So if you think about a randomly selected family, either they have a black and white television. Now this scenario is a very long time back story, right? Nowadays, you don't come up with black and white televisions, okay? Right. So either a household can have a color television set or a black and white television set, or maybe both, right? So what are those probabilities? Right? So you can say, let's say event A is the event that family in the metropolitan area owns a color television set. So what is PA? right? If you look at they are in respectively, so in order, color television set is 0.86. And what is B? When that family owns a black and white set. So what is the probability of owning a black and white set? That is 0.35. And then both kinds. So what is that? Both of them. They have both. They have a black and white and also a color. So what is that probability? 0.29. So what is the question? What is the probability that the family owns either or both? What does that mean? A union B. Either A, either B, or both. That is the union. So what they're asking is the probability of A union B. You straight away add the rule. You get 0.86 plus 0.35 minus 0.29. Okay? So what is the answer? The answer is 0.92. Right? Or you may say 92%. Right? Now, if you represent this in a Venn diagram, how do you do it? If you want to represent this in a Venn diagram, how can you do that? With the probability. Say A, the colored television set, B, the black and white. How do you fill this Venn diagram? Right? So when you fill a Venn diagram, you start with the intersection, the overlapping area first, which is 0.29. So this overlapping area is 0.29. Then what is the circle A? 0.86. So what is the value we should write here? This whole circle is 0.86. Out of that 0.86, 0.29 is already gone. So we have to subtract that. So what is the remaining value? You get 0.57. So that value should go here. So 0.57 plus 0.29, the whole circle, 0.86. Then for B, whole circle is 0.35. Out of 35, 0.29 is already there. So you have to subtract that 0.29. That is the value. 0.006. Sorry, 0.06. Right? Is that all? Is the Venn diagram complete now? What is missing? Yeah, the outside. Outside the circle, the whole rectangle, the sample space should be 1, right? But if you add 0.57, 0.29 and 0.06, you get this 92%, 0.92. So what is the rest? The rest 0.08. Where should you put it? Outside the circle, but inside the diagram, right? Now this is the complete Venn diagram according to the scenario, right? So when you do these type of calculations, always look at the values you get for probabilities. You cannot get or exceed 1, or you cannot have negative values, right? And always the sample space should be the total probability 1, right? Keep that in mind and make sure that all the conditions are satisfied when you get the final answer. Okay, right. Okay, so any question about this example? Now let's generalize this theorem for 3 events, right? So if you have A, B, and C, okay, how do we find the union? Not even for 3, you can do that for any, right? So let's expand it to 3 cases. Here are 3 circles. So how do you find the union? You get the probability of A, B, and C, right? That's okay. Then you have to subtract the overlaps of 2 circles. So overlapping of A and B, that's this one. So that is the intersection B. Then the overlap of A and C, this area, fine. Sorry, this area, right? And then B and C is this area. This is A and C. So you subtract the overlaps of 2 circles. And when you are doing that, what happens? This area, overlap of all 3, that area was gone. So you have to add it back. So plus the intersection, B intersection C, right? So there's a pattern you can see. First you start with adding the individual circles, then you subtract the overlaps of 2's, then you add the overlaps of 3's. If there are 4 circles, what will happen? You add the 4 circles A, B, C, D, then you subtract the two overlaps. There will be many, not only 3, right? And then you add 4 overlaps, then you have to subtract the 5 overlaps, right? So that is how it will go, right? Anyway, you can prove this one, right? Just what you have to do is change the sign each time, right? So he start with pluses, then minuses, then pluses, right? So the proof is here. I leave it as an exercise for you to look at it, right? That's not hard, right? That is applying the addition rule for 2 events, right? By writing A union B union C as 2 events, right? So this is 1 event, B union C, 1 event. So now this is like the addition rule for 2 events. So you have PA plus P, this part, minus the intersection of A and B union C. Right? So likewise, you continue with, you do the same with, and then you distribute it. Then again, you apply the same thing again and again. At each step, you can end up with this generalized expression, right? Right. So that's about the axioms of probability, and there are a few other examples that you can do with the combinations and the probabilities, right? So those are just some exercises for you, brainstorming. You can try them. I will upload this note set today. With that, we conclude the second section of chapter 2, axioms of probability. Okay. I can do one more example before we finish very quickly, which is an example for the union of 3 events. Right. I hope you can see the screen now, the session. Let's do this together. In a group of 150 students, 40 are registered to math courses, 75 for bio, 80 for history, 15 who follow math and bio, 17 who follow math and history, 30 who follow bio and history, 10 who follow all 3 courses, right? And then you have to find the probability of each of these events. So the first thing you have to do is, easiest is to draw the Venn diagram and fill the places. Then you can very easily figure out the probabilities they are asking, right? A group of 150 students, so that is our sample space total, right? So let's keep that in mind when we calculate probabilities, we will need it. So here's our mathematics, bio, history, right? Where do we start? From where we are going to start with the overlap of all 3 courses. There are 10 who follow all 3. So that 10 will go here. So let's go reverse. 30 who follow bio and history. Bio and history 30. So this area is 30. Out of 30, 10 is already there. So this will be just 20. Okay. So correct me if I make a mistake. Follow me, right? Then 17 who follow math and history. Math and history 17. Out of 17, 10 is already here. So 7 will go there. Fine. And then 15 who follow math and bio 15. So 5 plus 10, right? Now the rest you have to figure out, right? 75 for mathematics, 15 and 7, what is it? 22. So 75 minus 22 should go here. What is it? Am I right? Okay. Then 80, sorry. Oh, sorry, it's 40, right? 40 who registered for mathematics. Out of 40, you have 22 already gone to these places. So the remaining is 18, right? And then 75 registered for bio. Out of this 75, 20, 10, 5, 35 already gone. So only 40 will be here. And then history. How many? 80 are for history. Out of that 80, 37 already gone. So the remaining will be 43. Right. Now add all these circles and see whether you can get 150. If not, the rest should go outside. Right. So quickly do this calculation. We have to finish the lesson now. History 18, 40, 18, and 5, right? So 7 should go outside. Am I right? Right. So double check these answers. So you can find this probability, right? So what is the probability? Only one course, 40, 18, 43. Bio only, maths only, history only, out of 150. What is the maths only? 18 out of 150. History or bio, you have to find it, apply the addition rule and find it. None of the courses 7, right? Right. Okay, so with that, let's finish the session for today. I will upload this note set and we'll see you next week with the next section of chapter 2. That will be the conditional probability.